So, this is going to be lambda y plus lambda plus a y, right. Then I am going to get what 1 y. Is that right? Yes. Okay. But if it is to be in the same subspace, okay, this is not in V1. This belongs to V1 only if A is 0. But that is one fixed element of the group. Okay. So, this proves the result. So, these translations on a line represented on a 2-dimensional vector space cannot be fully reduced. Okay. Now, some of you may be familiar, but there are lots of representations which occur in physics, okay, which are already irreducible. So, let me give examples of irreducible representations. These are examples, okay, which are of relevance to physics. Okay. So, the 3-dimensional representation let me call it dr. It is simply r of rotations. Representation is d. Okay. It is a self representation. This is irreducible. I will prove later. It is not completely trivial to prove that it is irreducible, but we will tackle similarly. Okay. Similarly, the 2-dimensional representation, self representation of SU2, etc. Or if you are familiar with the angular momentum J representation of SU2 or dJ matrices, okay, they are all irreducible. There are many others. In fact, later we will see that we will mostly encounter only these things. Okay. Now, here is a theorem before I prove Schur's lemma. Okay. Can be written, said in many ways, okay, but I will write it here. Let H be a Hilbert space script H, okay, with scalar product let me put the scalar product like this. Okay. You are supposed to put entries here, alpha, beta, whatever. Okay. Let gamma put the UG, G is in some G, okay, be a unitary representation. So, the crucial word is unitary of G. Okay. Then gamma is a direct sum of gamma I, where gamma I are irreducible gamma I are irreducible. Okay, so you can completely decompose it into direct sum of irreducibles. Also, okay, if H is summation Hi, where Hi carries IRR comma I, this sum here, so this is sum, this sum 1 is an orthogonal direct sum. You know what that means? This phrase, you know what it is? So obvious, vectors are, so if that is, if xi belongs to Hi, then xi yj, say xj is 0, I not equal to j. So if you have a unitary representation, at least certainly in finite dimensions, you can take it apart into direct sum of irreducibles. So every unitary representation is built up of irreducible representations. Okay. Okay. In the finite dimensional case, the proof is rather easy. So let us see how it goes. Okay. The proof is as follows. Okay. 1. If H is a Hilbert space, okay, and H0 is a subspace, okay, there exists H1, okay, orthogonal to H0 such that H is H0 plus H1. You can decompose a Hilbert space uniquely into a direct sum of, if you give me one subspace, I can find the orthogonal subspace uniquely. Remember that, for example, in 2 dimensions, if I gave you the subspace consisting of vectors like this, okay, vectors like this, the complementary space is not fixed. For example, I say the complementary space can be anything like this, right? Can be anything for any lambda, fixed lambda. So if you give me the subspace, I won't know the complementary subspace. It is not fixed. But if it is a Hilbert space and I require orthogonality, it is uniquely fixed. Do you know how to prove this? The proof is as follows. Okay. One way to prove it is as follows. Okay. For let's say E1 En be an orthogonal basis. Well, there are several ways of proving it. Okay. For Gram-Schmidt, do you know Gram-Schmidt? You know Gram-Schmidt method? Yeah. So there exists an orthonormal basis E1 up to Ek, Ek plus 1, Ek plus n, right, where this first set E1 Ek, okay, spans H0, the rest Ek plus 1 Ek plus n spans H1. Yeah. So that completes the proof, because so I know what is H1. You choose this basis, okay, and the span of this will give you H0, and take the orthogonal basis, okay, which by Gram-Schmidt, by writing those Gram-Schmidt determinants, you know what they are. Take their span, you will get H1. That's it. So this decomposition to orthogonal subspace is always possible for a Hilbert space. The second statement is, if U is unitary, okay, and H0 is invariant under U, then H0 is invariant also under U dagger. That is because U is unitary, okay, because what I know is that U sends H0 to H0, okay, and this has to be onto, because U is invertible, and 1 to 1 and onto, okay, and U is invertible. Right, with U inverse is equal to U dagger. Okay. So it is going from here to here. So apply the inverse, it will bring it back here. Right. So if U is has this because of this property, H0 is invariant by U means it is invariant by U dagger. Okay. So this means H1, okay, if U H0 is H0, then U dagger H0, let us say U H1 is H1. U will then, if U leaves H0 invariant, it will also leave H1 invariant. Why? Can you imagine why? So what I have to prove is, for if X is in say H0, Y is in H1, then we know that xy is 0. Okay. To prove x, I have to prove uy is 0. Okay. I have to prove, okay, all x in H0, all y in H1. Right? How will I prove it? Put move u on the other side, okay, to prove this, but x u y is u dagger x y, right, and this is in H0, which by what I proved. So this is 0, right. So now we apply this result in the following way. Okay. Let us say 4. Okay. So if there is a subspace H0 is invariant by the representation phi of G, okay, and it is a unitary representation, okay. So it is orthogonal complement, okay. So is its orthogonal complement. H1. Okay. So I can write, so I have written H as H0 plus H1, okay, and both are separately invariant by the representation. Now how will I do? Maybe both are irreducible, then I have nothing more to do, but if it is either of them is not irreducible, there is an invariant subspace, so you repeat the process, okay. That's so if either is reducible, repeat. Okay, until you have put the whole thing as a direct sum of irreducibles. Okay. This is very similar to how you prove if you that a self-adjoint operator can be fully diagonalized in finite dimensions. Okay. All that you have to do is to prove that has one eigenvalue. Okay. The same proof can be used, for example, to show if you give me a self-adjoint operator K on a finite dimensional Hilbert space can be completely diagonalized, because what I will do is in finite dimensions, then because I will look for one eigenvalue, and by that always exists because the characteristic polynomial has at least one root, okay, and it will be real because K is self-adjoint. Okay. So you have one dimensional subspace where K is diagonal. You take the orthogonal complement, go on repeating, okay. You will find the whole thing splits up into a direct sum of one dimensional subspaces which are eigenvectors. Okay. So this is the quickest proof for showing that a self-adjoint operator can be diagonalized, and it is the same thing that we are doing here. So now what I want to prove is this. I want to prove this grand theorem. Okay. So I want to prove Schur's lemma. Okay. Let me state the theorem, then I will come back and give you some preliminary results to prove it. Okay. This is really a very central theorem and very simple. Given IRRs, this is important that they are irreducible representations. Okay. Gamma A by some linear operator is dA of G, gamma B dB of G, on, so there are two parts, one on vector spaces, okay, VA BB if there is a linear operator S, okay, S is taking you from VA to BB, so it could be some rectangular matrix a priori. It's a linear operator, but its domain is here. Okay, so linear in the vector is here, but the values are here. Okay. So it's some could be a rectangular matrix, or VA may be VB. Everything is possible. Okay. So if it has a property S, okay, dA of G is dB of G S. So, here I first apply dA of G and go to the vector space. So, this is on VA, take a vector in VA, okay, this end up in VB. Here I will first go to VB with S and apply G, okay. It has S as its property. These are irreducible representations. So, we say S intertwines the two IRRs then the claim is then either S is 0 or S is invertible and for the equation I have written down dB of G is S dA of G S inverse. The two representations are equivalent. Okay. Two, that is the two IRRs are equivalent. What is, there is some an excluded case here. Can you see what I am excluding the possibility? There is one class of this theorem is not empty. There is some whole lot of cases I am saying cannot happen. What are those cases that cannot happen? Where that will happen if S is singular but not 0. Cannot be. So, this is cannot be that S is singular but not 0. There are only two extreme possibilities, either it is 0 or it is invertible. Okay. Cannot be that it has one eigenvalue which is 0, that is impossible. Okay. The second part is the following. Okay. Same result. Okay. In this case, if a linear operator in this above case, okay, T, now I will take from VA to VA, okay, in above case, commutes with all DAG so suppose I have here I am specialized into the case but the domain and the range are the same. What will happen is T is a multiple of identity. That is T is of the form some lambda 1, lambda some fixed number. Okay. These innocent looking theorems are so powerful that you will be able to get orthogonality of special functions, the D if you are even the orthogonality of the YLF functions with all normalizations you can get, okay, without doing any calculation, without knowing what they look like you can get, okay. For all groups you can get, and you can tell the entire structure of the representation theory, general representation theory of finite and compact groups, all kinds of things. Okay. In the infinite dimensions situation is much more complicated. Okay. So, this looks very simple, and how will I prove it? The proof I am taking from Weil's book. At least the proof I found, which I found, maybe others, the proof I found was in Weil. Okay. It's classical groups, chapter 5. So, what I want to show is, as a preliminary, okay, let L, okay, be a linear operator from B to W. There are two elementary definitions. The null space, you know what it is? NL of L is what? All the vectors which it annihilates, okay, is a subspace of V, okay, set of all x in V, so that Lx is 0. Of course, the 0 is in W. So, it are all the vectors it kills off. The range RL, okay, is just the image, okay, is okay, simply LV. So, this is all vectors which can be written as Lx, okay, x is in V, is what you get out by applying L. Okay. Then we have the map L is 1 to 1 okay, if and only if the null space consists of the 0 vector. That is obvious, isn't it? Huh? Because if they, I can leave it if their null space are non-empty, it cannot be 1 to 1 because I can add it on to any vector. Okay. So, there will be more than, okay. So, this onto, okay. So, I will leave this as an exercise. Okay. It is a trivial exercise. Onto, by definition, if RL is W. That is obvious by definition. Okay. So, L is invertible if and only if the null space consists of the 0 vector and the range consists of all of W. So, again obvious. As an aside, it is amusing to know note, okay. If L is invertible, it is also true that dimension of V is dimension of W. Again, I can leave this as an exercise, namely the dimension of a vector space does not change under invertible transformation. You can prove it in infinite dimensions. Infinite dimensions, the question of counting comes. You can prove it in many ways. So, the dimension is an invariant of the vector space. Okay. So, that is the only invariant. Okay. can prove it by, let us say, for A, okay. Let us say if E1 Ek is a basis for V, okay, then if Y is in W, I can write Y as Lx, where x is here, but I can expand x in this basis. So, it is L of summation psi I E I but this is a linear operator. So, it is psi I L E I So, I know that L E I is complete in W, because any vector y can be expanded like this, or L E I is complete in W. Complete means any vector can be written as linear, but it is also linearly independent. Okay. Also, okay, if I try writing eta I L I L E I equal to 0, where eta are complex numbers, I have to prove linear independence of these vectors. So, this is the same as L acting on implies L acting on eta I E I is 0. Okay. So, what do I say? L is annihilating this. So, it is in the null space, right? Eta E I is the null space of L, but there is only one 0 there. So, this means eta I E I is 0, but these are linearly independent. So, this implies eta I is 0. Yes. So, I have proved, or L E I is a basis for W. So, since the number of, so one basis maps to another basis, so the number of elements you can just count. Okay. So, the dimension of the vector space does not change under linear transformations which are invertible. Is in fact a finite dimensional vector space, the only invariant, no matter how you present a finite dimensional vector space, the only invariant which completely characterizes the vector space is its dimension, in when you are dealing with real or complex vector spaces, there is nothing more. Now, what is Weil's proof? Back to problem, or sure, back to sure. So, in the sure case, we had an operator, what is it called, S. Okay. We prove the following things we prove. 1, the null space of S which is the original space V A. So, this is contained in V A. We will prove is invariant under this representation gamma A. By invariant under gamma A means every matrix linear operator in gamma A, but gamma A is irreducible. What does it mean then? it is an invariant subspace in VA, but gamma A is irreducible. There is no, so what can I say about, because of irreducibility I could say that this null space is either 0 or the whole space. This implies null space is 0 or the full space VA because of irreducibility. But VA is impossible because then L will be 0. Okay. So, excluding, so assume we can taking S not equal to 0, because S equal to 0 nothing to prove, we can immediately say that the null space consists of 0. Right? I will prove this. I will prove to you that the null space is invariant. There is a 2-line proof, but let me show you the idea. Second, we prove RS is invariant, is contained in VB, is invariant by under gamma A, under gamma B, which is irreducible. Okay. So, I have only two possibilities, namely R of S is either VB or null vector, okay, or 0, which will imply R of S is equal to VB or consists of 0. But this will mean that S is 0. So, as S is not 0, because we will not worry about that, okay, RS is VB. So, the null space of, if S is not 0, the null space is 0, and the range is the full space. So, either S is not 0 or S not 0 or S invertible. That is it. Okay. This proves the theorem, but no, except that I had to prove item 1, two items. How do I prove item 1? Okay, proof of 1. I take that X be the null space. So Lx is 0. So I look at consider, I think I called it I do not remember what I called the matrices of the representation. Gamma A is dA of G X. Now I apply L here, S here. I called it S. I apply S here. Can you guess the proof? S intertwines the two representations. So I can shift, write this as dB of G Sx, because S intertwines the two things, but Ss is 0 by this. So this is 0. That means DAG belongs to the null space. Right? Because I can shift the things. So I proved that the null space is invariant under the irreducible under this representation. Now I prove 2. Okay. If y is in the range of S, there exists x in the domain, right, in y is in the range of S, okay, there exists some vector x in the original vector space V A such that y is equal to S x. Right. Now, I want to show that the range is invariant. Okay. So, I look at dB of G on y idea is the same, is dB of G S x, but this beautiful intertwining property lets me shift around S dA of G x, so call this x prime, which is in V A, because this is a x and I am applying an element to the group A. So, we prove that this is whole vector is in V is in the range. Proof is finished. Okay, that's it. Okay. So, it uses extremely elementary properties of maps to establish this result. Okay. And as I told you, it is the range of its utility is amazing. Okay. So, today as a last statement, I will prove to you one very simple result. Okay. Using this, then we will conclude this part by giving you some operations with groups and representations before we start looking at finite groups in more detail, unless you have questions here. Okay. So, I want to show you that an example. Every irreducible representation of an abelian group is one dimensional. Remember, abelian group is group elements commute. The important thing is it is irreducible. For example, for translation we already saw a two dimensional representation. So, how do I prove it? Okay. Oh, I forgot before I finish. Okay, there is another part to Schur's lemma. I will come to this. Second part of Schur. Forgot to say that. Okay. Namely, this is a case where DAG is DAGT implies T is a multiple of the identity, right, for all G in the group. I forgot to prove that. No matter what T is, because it is in finite dimensions, for T has at least one eigenvalue called a lambda, such that T minus lambda times unit operator on some vector x is 0, okay, for an x, for eigenvector x. At least one. It may not have a complete set of eigenvectors, it may be of the Jordan canonical form, okay. I do not care, at least one eigenvector is there is, but this means T minus lambda 1 is singular. Its determinant will be 0, right, but it commutes, but minus lambda 1 times dA of g is equal to dA of g t minus lambda 1, because 1 does not do anything. So, this operator commutes with dA and it is not invertible. So, the only possibility is it is 0 by sure, the first part is sure, that means t equal to t minus lambda 1 is 0, right. So, we prove that in an irreducible representation, if something commutes with everything is a multiple of the identity, it is a corollary of the first part of sure. Okay. So, I want to give that back to the example, then we will stop. Okay. It is rather easy proof. Okay. If we are given that the group is abelian, okay. So, let its abelian group G to dG be an irreducible representation of our group, okay. Abelian group. Okay. Fix, take an H, then dH dG is equal to dG dH, okay, by abelianity for all G and fixed X for any H, for a fixed H, for an H. For an H this commutes like this, but this is irreducible. So, all by sure, part 2 of sure, dH is some lambda of H, one dimensional, just one of dimension 1 cross 1, otherwise it will simply be multiple copies of the same. So, I have proved. So, every irreducible representation of an abelian group is one dimensional. For example, if you take translations, example, translations, okay. Let me take A1 up to AN, and IRR is what? A is represented by exponential lambda I AI. Okay. So, let me call it d of lambda is this, okay, where lambda is a label lambda n. If in case lambda is purely imaginary, you get a unitary representation, okay. That is, if lambda is unitary, if lambda is lambda I pure imaginary, the IRR is unitary, okay. Otherwise it is not. So, the representations of the translations are in one to one with complex numbers, okay. We normally deal with unitary ones, say plane waves are these are momenta, okay, and they are unitary representations given by phase, but translations have many other representations which are not unitary, okay, and which are not irreducible. For example, I gave you some, and in particular there is the case where I am trying to remember the Laplace transform that people are, I mean this kind of thing when lambda is not real, you know, pure imaginary, does occur in analysis, for example, the theory of Laplace transforms. Okay. If you have done some, but anyway, most often what we get in quantum mechanics or in wave theory, electromagnetism, are the plane waves, okay, and they correspond to unitary representations of translations. Okay. But there are all kinds of non-unitary representations of translations which do not play a big role in practical applications. Okay. So, I will stop here, and next time I will give you some simple operations using representations, then we will go into finite groups. Okay.
So, the representation theory of abelian groups is in some sense trivial.
It is not, it looks to me abelian groups. Okay. It looks to me trivial, but she may object, I do not know. Okay. Infinite dimensional, I do not know. Huh? Is trivial, no? Abelian, finite dimensional, unitary abelian.
Does it change for infinite?
Sorry?
Does it change for infinite dimensional?
This I do not know, because yeah, I would imagine yes, because infinite dimensional case, these spaces you are dealing with R infinity, infinite dimensional Euclidean vector space. So, the topology will come. Okay. What is a, you want a continuous representation, no? If you change the group elements a bit, what you are getting out should change a bit, no? So, there should be topology. My impression is that it will change, it will be deeply affected, okay? But I have not good control on that. In the infinite dimensional case, I do not know what happens. Okay?
To answer your question, I'd say that the irreducible representation of the abelian group is as interesting as the theory of abelian groups. But I mean, it's not vacuous abelian groups, because for instance, you can hook up from abelian groups the trivial representations. Interesting example, Heisenberg groups, which won't be abelian groups, which have interesting representation. It's just one of the fundamental ingredients of representation. It's the easiest understood. We combine it with these
I do not know this, because this kind of thing also comes in when you discuss differential equations. This what they call pseudo differential operators and so on, this stuff comes. Okay. I mean, you want to analyze, say, wave propagation, heat equation, that kind of thing, no? And very often we use Fourier transforms. It may be highly nonlinear. Then there is this so-called symbol of the operator, and there is some activity. So, when you start studying those practical applications, numerical applications even, these things come, and I do not know how they, from what I have heard, it can be quite complicated, but I do not know enough. So, next time I will give some examples, then we will go into, basically systematically go into finite groups, and then representation theory of finite groups, and I will end up with discussing representations of the permutation group in some detail. Okay. I will not discuss all possible finite groups, okay, but there will be enough that if you want to, you can do, I mean, go and check what kind of thing. Depending on interest, I will try to show you certain things which come in a much more sophisticated way in discussions of conformal field theories. There are those so-called fusion rules and so on. Okay. They all come here, but in a more understandable way for just finite dimensional finite groups. Okay. Fusion rules correspond to what happens if you take tensor product of two irreducibles and you decompose it into irreducibles. So, fusion rule is this: tensor, these are two irreducibles, right? So, unitary irreducible. So, you can decompose it into direct sum, right? You can write C alpha beta gamma gamma gamma. This is a direct sum. Okay. So, you are decomposing tensor product of two unitary irreducible into direct sum of irreducibles. these are called in physics literature as fusion coefficients. Okay. They are very important. The same thing happens in quantum field theory, where they come in what they call operator product expansions. Okay. And they have very beautiful properties, unexpected properties. Okay. But we can understand them already in the context of finite groups. Okay. They have properties of groups. Okay. There are some identities, pentagon identities, and if you take 3 of them and use associativity, you get identities and so on. Okay. They are, as I say, quite surprising and of great use also. But so depending on time and interest, I will do it, or I may jump to Lie groups after I finish the finite groups.